Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about protecting groups. How that protecting groups is what are the common protecting group used in the carbohydrate chemistry, how the coupling efficiency and how it can be utilized for getting the proper or the desired product. So that type of the discussion we had discussed yesterday. So today what we are going to discuss, let's see here, intramolecular glycosidation reaction. First of all, how do you define intramolecular glycosidation reaction? So intramolecular means the reaction occur within the molecule. So that kind of the reaction are generally termed as intramolecular reaction. Glycosidation, it is one of the process where the one of the sugar unit bind to the or attach to the another sugar unit and resulting compound may be as monosaccharide, disaccharide, trisaccharide and so on. So that type of the processes are known as glycosidation process, and that after the glycosidation whatever the product obtained which are known as disaccharide, trisaccharide, these are the derivative, and that the reason behind it, the main object or the main purpose behind it, these type of the structure they exhibit great potential toward the biological activity, and therefore this is the recent trend in carbohydrate chemistry, and that's why the recent researchers paying attention more toward the synthesis of this compound, and therefore that type of the processes glycosidation, and these reactions are known as glycosidation reaction. Now let us discuss little bit about the introduction. Carbohydrate derivatives found in nature are almost always linked to each other by glycosidic bonds, and there has been increasing interest in the synthesis of biologically active oligo and polysaccharides, and reliable methods for the formation of glycosidic linkages have been the subject of intensive study. Two problems are usually encountered in the synthesis of a glycosidic bond: unreactive hydroxyl groups and lack of distereoselectivity, that is the formation of alpha and beta epimers. To overcome these problems, in the last decade, chemists have explored a new approach, intramolecular glycosidation reactions. In this review, we will define the term intramolecular glycosidation reaction as a type of reaction in which the glycosyl donor the glycan is linked to the glycosyl acceptor, the aglycan, by means of tether producing a O-glycosidic bond, which is represented in scheme number 1. Let us see that scheme number 1, which is represented over here, this one. Now let's see X, which is present over here, and here this is a RO, just as a protecting group introduced in that, and which is known as glycosyl donor. This is called as a glycosyl donor, and now this glycosyl donor will be treated with glycosyl acceptor. Here is R is shown over here, and the resulting compound, this is a glycosyl acceptor, this one, and when they coupled together, this is known as tethering procedure. This is a tethering procedure. This is a tethering procedure where you can get this type of the reaction over here. You may get one structure like this. Here X, which is represented in structure number 1. Here this is a protected group RO as it is, and now then it is shown another structure which is here. This is a R, generally is a RO, not the R. RO, alkoxy type of the groups. Then there will be here T1 is called as a T1 tethering, and after that there is one process. This process is known as a glycosidation process. This is known as a glycosidation process. Glycosidation procedure, we are going to get the resulting compound is a disaccharide. It's a disaccharide, and in the other way we can write here another structure the same way. Here RO, then here is another structure shown over here, that is here hydroxy group. Here this is known as a T2, is again once again tethering group, that is a glycosidation procedure. Now after the glycosidation procedure, glycosidation procedure, the resulting compound obtained will be tethered disaccharide. This is known as a tethered disaccharide, tethered disaccharide, which is a compound which we got over here, and this is known as scheme number 1, which is represented here. This is a outline of tethered intramolecular, outline of tethered intramolecular glycosidation reaction. Intramolecular glycosidation reaction, and which is represented over here. Here T1 is known as a temporary tether. Here that T1 is nothing but as a temporary tether, and T2 is nothing but as a stable tether. T2 is known as a stable tether. This T2 is a stable tether, and T1 it is a temporary tether, means that blocking of that group whenever we require as a desired product, we can easily remove it, and that's why it is known as a temporary. But if the stable tether is there, we cannot remove it as per as a requirement. So reactions in which the tether participation in the reaction tethering to the glycosyl donor, that is a carbon tether. In 1991, Baresi, the scientist named Baresi and Hindsgool reported the first example of an intramolecular glycosidation procedure and introduced the expression intramolecular aglycone delivery. The idea was to use this approach in synthesis of 1,2,6 glycosidic linkages in the difficult anomeric case. The setup for this reaction was thioglycoside 1, a glycosyl donor with a 2O acetate group, which is represented in scheme number 2nd. Now let's see over here how it can be useful as far as this intramolecular glycosidation reaction is concerned. Let's see over here, that is the structure number 1, which is nothing but as a thioglycosides. As we know that at anomeric carbon atom there is a sulfur, that type of the group is introduced, that is called as generally the thioglycoside. This is nothing but as a structure number 1, where at 2 position there will be these acetate groups are present. Now all other group which are lying equatorially, that is protected by benzyl group. Here OBN, so we can write OBN once over here. Now this thioglycoside will be treated with this thioglycoside can be treated with Tebe reagent, that is a Tebe reagent. As we know that Tebe reagent, one of the complex reagent which is specifically is known as a regioselective reaction. As we know that regioselective reaction means what? The question start from where it will react. It will react at the specific region, and therefore that type of the reagent is called as a specific. So this is a Tebe reagent. Speciality of this reagent, the ester carbonyl group can be converted into as a olefin. So that is the speciality of this reagent. Other thing remains as it is. So we can show over here this thing as it is, OBN, this one also as a O as it is. Here this is oxygen atom. Here you can bring, observe this structure and this structure carefully. Most of the students in hurry, they can show as a O oxygen. Remember, this carbonyl group is converted into as a olefinic group. That the changes, that is the speciality of that Tebe reagent, and this other part remains as it is. Here is the SET, that is the thioglycoside, which is a structure number 2. And this further treated with alcohol, ROH, and the catalytic amount of this one TSOH, paratoluene sulfonic acid, and this reaction takes place at minus 40 degrees centigrade and stirred for 20 minutes, and the resulting product obtained will be this one. Now here we are going to get the product. Other part remains as it is, OET. Here this OBN, which is also remains as it is, OBN also remains as it is. Here OBN also remains as it is, but here there is this oxygen atom. Now this olefinic group becomes as a methyl group, one above the plane and one which is below the plane, and this remains in the plane, and that is represented in this manner, and this will be the structure number 3. And after that, this compound further treated with this one, generally NIS, n-iodosuccinamide, and the base is used here, and base is used, and this reaction is stored for 16 hours. A reaction completed within 16 hours, and the result, and this is used as a 5 equivalent of n-iodosuccinamide stored for 16 hours, and the resulting compound will be obtained as this one. Here structure number 3. Here is a OR, not this one. That is a OR, because we are adding as alcohol, so that we are getting as this one. So OH like this, it is attacking over there. So methyl group, and that also becomes as a methyl. One goes above the plane, one goes below the plane, and O remains in the plane. And after adding these reagents, we are going to get this type of the intermediate here, and the intermediate will be this one. So other group we can show as it is, OBN, then OBN, here O, here also O, then one group below the plane, one group above the plane, one is below the plane, and we can show over here this. You can join oxygen atom over here like this, and R, that is a positive charge, and this is a structure number 4 we can show. And after adding water or in work of, and the resulting compound obtained will be the structure number 5th one. So here at equatorial position there is a OR, glycoside is obtained over here, and here OH is a free and other are the protecting group, and they are written as it is, and this will be the structure number 5. If you see this scheme carefully, that is the scheme number 2 represented over here. It's a scheme number 2nd, that is isopropylidine tethered glycosidation is shown here. The acetate was converted to methylene active derivative 2 with the Tebe reagent. As we know that Tebe reagent, how it is prepared, so that is a separate, you can see in the organometallic compounds. And now treatment of 2 with the alcohols A, B or C in the presence of catalytic amount of acid formed the key acetate, that is the 3A to 3C in a moderate yield. Activation of 3A to 3C in moderate yield. Activation of 3A and 3C with 5 equivalent N-iodosuccinamide. In short, it is written as NIS, resulted in selective intramolecular glycosidation at the beta phase via intermediates 4A to 4C, which on aqueous workup gave the desired beta monopyranoside 5A to 5C. A similar approach was taken by Ito and Ogawa, these are the scientists' name, who introduced paramethoxybenzyl PMB, shortly written as carbon tether alcohols protected with PMB. For example, structure number 6 can be actively oxidatively deprotected with DDQ or and presumably via the oxocarbonium intermediate, structure number 7, scheme number 3 represented over here. So how it can be used as an protected group for alcohol, that is shown here. Let's see that also here, that as we know that general formula of alcohol is ROH, and this will be treated with this compound, as we know that OMe paramethoxy benzyl chloride or Cl. So the reaction carried out according to as a SN2 type of the reaction, and you will get the structure is this one, OMe, then here OR. Then this is further treated with DDQ. DDQ means what? Dichlorodicyanobenzoquinone, and the intermediate will be formed like this, OMe plus, then double bond O, or we can write, and this compound further treated with water gives, this is a side product OMe, there is a aldehyde group CHO, and we will get back is a ROH. That is a deprotection can be done very easily. That is a scheme number 3. This is a scheme number 3 which is represented here. That is a protection and deprotection of paramethoxy benzoyl chloride ethers. The basic idea was to trap intermediate structure number 7 under anhydrous condition and react it with another alcohol, producing the corresponding mixed alcohol, mixed acetal. The author showed that treatment of manosyl donor structure number 8 with DDQ and alcohol A2C gave the mixed acetate 19A to 9C scheme number 4. Without purification, 9A to 9C were activated with AgOTF and SnCl2 in the presence of DBMP. DBMP means 2,6-ditertiary butyl 4-methylpyridine. An aqueous workup gave the expected beta-mano pyranoside 10A 10C in a good overall yield, and which is represented over here. Let me show that scheme also here. So let's see that one also. Very briefly we are discussing this one. Here there will be a what we can call it as a F, and now there is a O, P, B, M, and not PMB, paramethoxy benzyl chloride, and other part they are the protected by benzyl group which is represented like this. This is a structure number 8, and which will be treated with DDQ, as we know that dichlorodicyanobenzquinone, and then you will be getting here this type of the structure. Once again O, here you can write F as it is, but here the O, and similar way we can show this one. Then there will be OMe positive charge, and other part OBN, and this OBN there remains as it is. And now when it is treated with ROH alcohol, what do you get? Resulting compound will be of 10 here as this one. Other part remains as it is here, only O, OR. Here is a what we can call it as a, this one remains as it is, OMe. This part, other part remains as it is, whatever initial group. So we can show that as it is. This is represented in a square bracket, that is as an intermediate. This is structure number 9, and when it is treated with the reagent like AgOTF, that is a silver trifluoromethane sulfonate or silver triflate in presence of SnCl2, tin chloride, and DBMP gives the product this one, Here is a OH at equilibrium, OR, that is a glycoside. We are generally getting OBN, other OBN, here also OBN. So this is a structure number 10, that is nothing but as a glycogen, and this is the scheme number 4, which is represented over here. So that is a PMB theta glycosylation in the synthesis of beta mannopyranosides. So I think with this we have completed the whatever point regarding as the intramolecular glycosidation reaction that we have seen with the help of some examples. If you see here, as we know that the structure of here is a DDQ. You might be knowing as the structure of DDQ is this one. This is a structure of DDQ CN, and here is a chlorine, here also has a chlorine, and therefore if you number from this 1, 2, 3, 4, 5 and 6, you can remember 2, 3 dichloro at 5 and 6 position, 5 and 6 dicyano benzoquinone, which is the name of this compound, which is a very good reagent used to remove this PMB. So I think with this, let us stop today here. The last point I think remaining in this course is the total synthesis of that oligosaccharide. So that we will see in the next lecture. With this, let us stop today here. Thank you. Have a nice day.